So what I'm going to talk about today is, I would say, like I will report on recent progress on the problem of existence of sub-Riemannian geodesics. So this is maybe what I'm going to talk is a collection of 3-4 papers. I don't remember something. It all started with Andrea Agrachev, and then something with Alessandro Gentile, and with Francesco Boarotto, and with Luca Rizzi, and with Andrea Mondino. Okay, but I will say maybe who are the actual authors in every case. So I'm going to talk about variational problems, and for me now this is going to be a bit. I'm going to be a bit loose on the topic. Okay, so our main interest will be in the problem of finding geodesics on sub-Riemannian manifolds, okay? But I want to just start with some examples to understand what we're going to talk about. So there's going to be some topology coming into the game, okay? And some of the ideas are come from mimicking constructions in classical Riemannian geometry. But then in the end of the talk, so in the second part of the talk, I will show that there are actually new ideas coming from the very special properties of sub-Riemannian manifolds, okay? So basically, roughly speaking, for me, variational problem means I'm given, say, a function on some topological space, and I want to minimize this function, okay? So this is very vague, very loose, but in most of the cases, in the classical cases, X is a Hilbert manifold, okay? And J is a smooth function. Hilbert manifold means that we don't necessarily have need our manifold to be finite dimensional, okay? So just to give you some stupid examples. So example 0, it's 0 because this is finite dimensional, is we want to find the minima of a function defined on a smooth manifold, okay? In fact, when I said I'm going to be a bit loose, it's because I don't want just to find minima, but in general, like critical points of a function, okay? This is example 0, so, and this is very well studied. Basically, like if the function j is generic enough, this is basically Morse theory, okay? The way that topology of the manifold interacts with the critical points of the manifold, of the function j. So maybe example 1, a bit more interesting. Example 1, so this is infinite dimensional. So our space X is going to be the set of paths on a manifold, Riemannian manifold, Mg. And these are going to be paths between two fixed points, okay? x0, x1. So it's important that these 2 points are fixed right now. And the function j is just, so it takes a path and gives the energy of the path. So of course, if I just say path is not enough, okay? I need to take paths at least absolutely continuous, and for which the derivative exists almost everywhere, and with derivative in L2 of any Lebesgue measure, in fact. And then this is like the functional you are interested. So what are the critical points of this functional? These are exactly geodesics in the between x0 and x1, okay? So curves which are locally length minimizers in the classical sense of Riemannian geometry. So maybe example 2. So you see, by the way, something I did not mention is that if I take really like absolutely continuous paths, all defined on the same interval, with the derivative which then exists almost everywhere, and which is of class L2, and I endow this space with the W12 topology. So this is a Hilbert manifold. So it's locally modeled on an L2 space, okay? So the function j in this case is smooth. It's just the part of the norm that we are using, okay? And the critical points, as I said, are... so this can be studied in somehow a classical way. Another example, X, you could take closed loops. So in this case, a gamma is a map from S1 to the manifold. And again, you can assume like some regularity, AC plus something, okay? Take this topology. Topology for now is not necessary, okay? And then J is again the same. So now in this case, critical points are closed geodesics, okay? So these are like curves which are locally length minimizers and are images actually of a circle. Okay, closed geodesics in this sense. Maybe there is an example number 3, example 3, which is the sub-Riemannian case, which is going to be discussed later. Okay, but just to keep in mind that simplest example, then there is like the classical examples coming from Riemannian geometry, and then what we want to focus on, the sub-Riemannian case. Okay. So now something I want to stress is like, okay, so our goal is basically to find critical points of a functional, okay? And the main tool, I would say, is the topology of the space where this functional is defined, okay? So I would say interaction between topology and critical points. So let's say the prototype for this is, again, Morse theory, the simplest case. So in fact, even like to force the existence of critical points, the prototype is Morse inequalities. So let's just stick for 1 second to this example, just to understand what I'm talking. So we have our manifold, okay, like this. So let me take this function, so this height function. So this function has 1, 2, 3, 4, 5, 6 critical points, okay? And so if I denote, so X is my space now, okay? Is this space? If I denote XE to be where this is less or equal than E, okay? So the classical Morse inequalities, which is the instrument, is that like the total amount of topology that there is in our space. So this B means the sum of the Betti numbers. Okay, it's just vague, but just to understand. So the total amount of topology in our space up to energy E is smaller than the number of critical points of J with energy less than E. So for example, if you take this level of the energy, okay, so the space we get is something like this, okay? So this space is homotopic to like a cylinder with one thing attached, which is like homotopic to this. So there are like 2 loops. One loop is here, and one loop. So one loop is here, and one loop is here, which are non-contractible. And then there is one component. So the total amount of topology here, this number I denoted here in this case, is 3, which of course is smaller than the number of critical points at level smaller than E, because there is 1, 2, 3, 4, 5. Okay, that's just a prototype. So there is no way, if you take your function, which is Morse function, that you can like reverse this inequality. Okay, it's a theorem. And it's a prototype because you see, you can either read this from left to right to control the topology, or read it from right to left to predict the existence of critical points. So because if you read it from right to left, it says that there is at least this many critical points. So if you can predict some topological property on the space, then you can ensure that like there are at least this many critical points. So maybe I should say again something more about like these critical points. So the meaning of these critical points is really like they are the obstacle, so the obstruction to deform your. So suppose I am at this level here, okay, and I want with minus the gradient of the energy to like follow this, deform my space and make the energy decrease, okay? At some point I have to stop, and the obstacle, the obstruction for this deformation are exactly the critical points. Okay, so critical points, it's the same thing in this case. These are the obstructions for deformation. Okay. So by the way, so this is the the finite dimensional case. So in the infinite dimensional case, in these 2 classical examples, still critical points are the obstructions for the deformation, but okay. So in this classical example, still critical points are the obstructions for the deformation, but they are geodesics in these classical examples. There is one more technical tool which is important in this infinite dimensional case. So we don't just need our function to be smooth and we know the general critical points, but it also has to satisfy some property that guarantees that you can make this deformation somehow, and this is so-called Palais-Maid property. So in infinite dimension, we need this property to be satisfied, okay? In fact, just to mention, using this approach, one can prove these two classical theorems about the existence of one closed geodesic on a compact Riemannian manifold and infinitely many geodesics on a compact Riemannian manifold joining 2 points. And the proof is this, essentially. It's based on forcing, so if the manifold is compact, this space must have enough topology. In fact, in this specific case, the cohomology of this space has infinitely many generator. And then it means that this number, if you want, is infinite. And then if you apply this scheme, which of course is infinite dimension, but it still works in infinite dimension, you predict infinitely many geodesics within 2 points. And in this case, a similar argument, but not on Berry numbers, but on the homotopy groups. So if the manifold is compact, somehow like there is one homotopy group of this space, okay, which is non-zero. And you do some minimax. You test your existence of a critical point against this homotopy class. Okay, so this is the scheme of what happens in infinite dimension. And of course, here one needs J satisfy the so-called Palais-Maid condition, which is basically what guarantees the fact that we can deform the space. Okay. So by the way, this is called Serre theorem, the existence of infinitely many on a compact Riemannian manifold between 2 points. And this is called Usternik-Fett theorem. Okay? So the existence of at least one closed geodesic on a compact Riemannian manifold. So now we come to the SubRiemannian case. Riemannian case. We come to the sub-Riemannian case. So now I consider, so notice this is not X, it's a slightly larger space. So omega is the set of, okay, suppose we are given M, which delta is a distribution, okay? And we have Riemannian metric on delta. Okay, so we have a sub-Riemannian manifold. This is quite general. And we look for, I consider just for 1 second, the space omega. These are all curves on the manifold, which are absolutely continuous. So the derivative exists almost everywhere, and is L2 in the distribution. So it takes value in the distribution. So these are absolutely continuous curves with the derivative, which is horizontal almost everywhere. Is it in the distribution almost everywhere? Okay, and is L2. So this is a shorthand notation for gamma dot. Okay. Is almost everywhere here, and it's L2. Okay, and also let me take. Let me say that gamma of 0 is a point that I fix y0. Okay, so these are all possible, admissible in the sense of SubRiemannian joint curves sorting from a point. Okay, so this starting point is just could be any point. Okay, it's not important in our goal. Okay, and now I denote, so now in my case this x, I denote it this way. It's the same thing, but I also want gamma of 1 is y. So this is basically the set of like horizontal curves joining y0 and y. Okay, so the set of curves between 2 points which are horizontal. And of course there is some, as I said, restrictions on the regularity of these curves. Okay, and I take this space again. I work with the W12 topology. Okay.
So the first one is an Hilbert manifold?
Yes, this is a Hilbert manifold. In fact, this space here. Yes, in fact, this space it's by itself a Hilbert space, Because if you take a global frame, you can, in fact, not just a global frame. It's okay, let's see. If there is a global frame for the manifold, it's a Hilbert space. Otherwise, it's a Hilbert manifold. It's just Hilbert manifold. It's a Hilbert manifold.
But you need to assume that delta is a constant dimension or it's a subbundle.
Okay, for what I say right now, yes, delta is a subbundle. For what I say right now, yes, delta is a subbundle. Okay, but you can work in a slightly more general framework. But for now, it's going to be a subbundle of the tangent bundle. Okay, and also I want to rule out the fact that we are in the Riemannian case. So I want that delta is bracket generating. Okay, so it's totally non-holonomic. And so the problem here is find geodesics, which now means locally length minimizers. Okay, so find horizontal curves which are locally length minimizers. Okay, so we call these geodesics. Okay, so the length of a curve is, of course, the integral of the modulus of the velocity. Okay, or if you want, the distance between 2 points is the infimum over our class of curves, of the length of curves. And locally length minimizers means that, like, I have a curve. For every point of the so it's a final sum interval. For every point of this interval, there is a small neighborhood of this point such that the curve is minimizer. Okay, maybe not the unique, among all possible horizontal curves joining the two points. Okay, so this is locally length minimizer, our definition. So by the way, this, if this manifold M, if the distribution here was the whole tangent space, geodesics is the same as critical points of this function. Okay, but here there is one new complication that we have to face, that this space here now needs not to be smooth. Is not necessarily smooth. Necessarily. So this is the first complication that we have to face. So in some sense, if it's not necessarily smooth, it's not even clear at this point what should be a critical point of J restricted to this space. Okay, and in fact, so when it is not smooth, it means in the language of sub-Riemannian geometers that there is inside this space one of these curves, which is not a regular point for the endpoint map, which is the map that takes a curve and gives the final point. Because just to give like a bit of a flavor of what's going on, let me put this small remark here. So here's what we have. You have this omega. These are all curves sorting from a point. And then we have a map, which we call the endpoint map, that takes a curve and gives the final point of this curve. Okay. On this space, of course, we have our energy. So now, if this point is not a regular value of this map, then the corresponding space, so the set of curves joining these 2 points, might be a singular space. In the Riemannian case, this is always a submersion, so every point is a regular point of this map. So we can in the Riemannian case, if I take a point and a direction on this point, I can always make a variation of curves such that the derivative is in this direction. In the Riemannian case, I don't have this constraint. But in the sub-Riemannian case, even if you stay at the origin, the image of the differential of this type of variations is just a distribution itself. So we have this. We might have this property. So this space is not necessarily smooth. So the one interesting thing, though, is that still we could say this is very interesting, that the set of geodesics, so curves which are locally length minimizers, is contained, okay, in this set, in the set of curves for which, so somehow they are so-called critical points for the so-called extended endpoint maps. But let's just write in this way: curves for which there exists this Lagrange multiplier, lambda mu, such that lambda differential of gamma mu differential gamma of the energy. So this is mu. Okay, so we can work in a slightly larger class. So if let's say if if gamma is a regular point for the endpoint map, okay, for this map here F, so this is the classical Lagrange multipliers equation. So this is the equation that is satisfied by a classical geodesic, in the case the space is smooth. Otherwise, it might be that we have something like this, that we have, for example, a pair lambda mu for which mu is 0. So we have something like this. That means that gamma is a critical point for the endpoint map, okay? And we still want to think like that this set, that like geodesics might lie inside here. In fact, it's a theorem. Like if you have a geodesic, it must be of this. It must be. It's not a characterization, but it's a theorem that if you have a geodesic, it must solve this equation, okay? It's like a kind of like a homogenization of the equation, okay? So it might be that like mu is 0. Okay, so you see that so if I still want to play this game here, like at least predicting some existence of critical points, starting from the knowledge of the topology of this space, I still would like to understand at least at first what's the topology of this space. Can I say something about the set of horizontal curves joining to these 2 points? Okay, and so let me say, I would say here, something about the structure of this space. Okay. So this is what is true. This is a theorem with Francesco Boarotto. What is true is that you can take the space of horizontal curves, okay, with this topology, so with the W12 topology, and include this space into the space of like all curves joining to point. Let me call this standard, okay? This is the set of like curves joining to point with no constraint, no holonomic constraint. And what is true is that this inclusion is a homotopy equivalence. Okay, so this was known in the case of the L infinity topology by a result of Agrachev, but here we want to work on a topology on which the energy is differentiable. Okay, it was proved in the W11 topology by Domini and Rabbits, that's the name, right? But still the W11 topology is not good because still the energy is not differentiable. So in order to have differentiability, you need of the energy, you need the topology to be at least W1. So this inclusion to be an homotopy equivalence, a W1P topology with P slightly larger than 1. Okay, and in the sub-Riemannian case, in fact, it's true for all P. This is true. Okay, so it's a homotopy equivalence. In particular, that means that like we don't, even if this space is singular, okay, still it's a homotopy equivalent to a smooth space. So in particular, for example, this space has the homotopy type of a CW complex. And maybe more pictorially, I would like to show it this way. Another consequence of this homotopy equivalence. So imagine like here you have your manifold M, and here you have 2 points, y1 and y2. Okay, so M is a sub-Riemannian manifold. And you look, and here there is your initial point, y. And you look for the set of all curves joining y with y1. Okay, so it might be that y1 is a regular value for the endpoint, so your space is smooth. Okay. Or it might be, for example, that at some point, the point y2 is a singular point for the endpoint. It's not a regular point, sorry. So your space might be singular, something like this. It might have a singularity. So this singularity here is a curve, which is a so-called abnormal curve. So what this result says is that from the homotopic point of view, you see no difference. So this space, which is very singular, has the same homotopy type as this space. They all have the same homotopy type. In fact, maybe more, we could even do a bit. So imagine that this is the classical one, so the space like of curves joining y with y1 with no constraint. So the inclusion of this in the classical one is homotopy equivalence, okay, also in this case. And all this space, so these middle ones, so these horizontal ones, they are all homotopy equivalent one to the other. Of course, when the manifold M is fixed. So this all depends. The homotopy type of this depends on M. But it depends on M in a very controlled way, which is basically like what is already known by Serre. Like you can compute, if you want, the homotopy groups of this space using the homotopy group of M. Okay. So in particular, you immediately see that, what is this here? Here. 1 second, what I wanted to say, yes. You immediately see that, for example, if you knew already that the point is a regular point for the endpoint map, you can just apply the classical machinery from classical like infinite dimensional analysis and predict the existence of infinitely many geodesics. Because after all, that theorem does not use the differential structure of this. It only uses the homotopy groups and or the Betti numbers of this, and they are all the same. It doesn't matter if it's horizontal or not. Okay, but of course, if it's singular, it's something more delicate. Okay, so now a special, already like a special feature now. So this is just to describe the topological structure of this space. Okay, so something I want to say is that we already noted that somehow like not all geodesics are critical point in our usual sense, okay? But what I want to say is that for the generic choice of the distribution, okay, only classical geodesics are obstructions for the deformation, okay? So if you apply some variational method on this local scale, whatever geodesic you're going to find is one of these classical geodesics. So it's called a normal geodesic, okay? So let me make this more precise. So maybe I can erase over here. So I want to at least rule out something out of this set, okay? So what I said is like in the classical case, obstruction for the deformations are the critical points. Once again here, critical points should be thought in this more general sense, okay? Not just curves which are, okay, not just curves. So it might be that, like, again, an abnormal curve, so a curve which is a critical point of the endpoint, might be a geodesic, okay? But I want to say that, like, at least in the generic case, these curves, they are not obstructions for the deformation, okay? So at least to say that, like, in the global, from the global point of view, if we do something like a global variational problem, whatever we're going to find is one of the so-called normal geodesics. So let me make this more precise. So, okay, so let's say obstruction for deformation are the so-called normal geodesics. So maybe first I can say a picture just to explain what I mean. Suppose you have this picture is again this picture if you want, but now I'm going to put the energy. Okay, in this picture there is no energy. It's just about the fibers of the endpoint map. So suppose you have now a point which is a regular value of the endpoint, and you have the space of all curves. I'm going to depict it this way, and you have the energy. So you can deform this space until you get to a normal geodesic, so a critical point of the energy. But suppose now you pick a point which is a critical, which is not a regular value for the endpoint, so your space might be singular. Okay? So what I want to make a bit precise is that in the generic case, even if there is a singular, an abnormal curve, at least in a weak sense, you can make this deformation. Okay, so this is what I want to make precise. At least in a weak sense, the abnormal curve does not affect the topology of the space. Okay? Yes, I want to make precise in which cases this is true, yes. So this is going to be true for the case where the rank is larger than 3, and in the generic case, so it's going to be true for an open, dense set of distributions in the Whitney topology, for the generic case. I can make these maybe, so we have actually a technical condition, okay, which is verified in the generic case, and maybe I can put a star, and maybe I can say something about what is this technical condition, okay? The fact that this our technical condition is valid in the generic case is a result by Chitour, Jean, et al. Okay, so what is the statement? So this is a theorem with Andrei Agrachev and Francesco Boarotto. And the theorem is this. Suppose you have, so I want to make precise this idea that if I have a cycle or something in this space, okay, at some energy, and I have no normal geodesic in the energy, even if there is an abnormal geodesic, I can move this cycle below the level of the abnormal geodesic, okay? I want to make this precise. And this is the statement. Suppose we have a continuous map from a compact, say, manifold to our space. Okay, so this continuous map can be, for example, embed a circle in our space, okay? And assume we are under this generic case, okay? Assume that there are no normal geodesics in the level with energy, say, let's call this E2, E1, E2, okay? So there are no potential obstructions in the classical sense for the deformation. Then, for every epsilon larger than 0, you can find a homotopy of map, okay, such that at time 0, it's just our f, and at time 1, everything has passed arbitrarily closed f of z, arbitrarily closed to omega y 1 plus epsilon, okay? It has arrived arbitrarily close to the level, to the energy level of E1, okay? So this means, in general, maybe you cannot make a deformation of the whole space, simply because what would be the instrument for making such a deformation? There's not even a gradient flow defined because the manifold is singular. But as long as you pick in your space something which is finite dimensional, okay, and if you have no obstruction in the classical sense, then you can push this finite dimensional piece. You can make it like a pass any possible abnormal geodesic. Of course, if the abnormal curve, okay, any abnormal curve. So, so let's say as a corollary from this result, I'm going to put it here. You have what we call the SubRiemannian minimax. Okay, I can discuss it later, but you can see already what it is. It means that, like, if you are doing, if you take something like the inf of the sup of the energy on some class of maps, okay, if this is non-zero, this must be almost the critical the level of a geodesic. Almost means because there is this epsilon, we might have a geodesic in a very close energy level. Okay, I can make this more precise, but first I want to at least draw a conclusion out of this, so maybe a real corollary. So this is now with no assumption, except at the rank, no assumption actually, sorry, corollary, no assumption. I claim that if M is compact, and I am given 2 points on M, x and y, then the following set has infinite cardinality. The set is the set of this set of curves solving this equation, okay? So the set of curves which are either normal geodesics or abnormal. Okay, so this set is infinite. Okay, so a priori we cannot rule out that there are infinitely many abnormal geodesics. We'll show an example in a second. So this is what it should be considered as really like the SubRiemannian analog of Serre theorem. Okay, because we cannot rule out that there are infinitely many abnormal geodesics. So I fix 2 points. Yes, between 2 points. Curves which are either normal, geodesic, or abnormal between x and y. Okay, this set has infinite cardinality. Okay, just to see that, like one example where we actually have an infinitely many like abnormal. Okay, we can take, it's a degenerate example, but it doesn't matter. We can take as an example a Martini case. Okay, so we have a Martini surface, and I want to assume on this Martini surface that the induced foliation has one closed trajectory. Okay, so then I pick one point on this closed trajectory. So this is the Martini surface. This is too small, maybe? Too small, you're right. So I'm going to go into this blackboard. Okay. So now this piece of the blackboard is a three-dimensional Martini manifold. Okay. So it's two-dimensional, but use your imagination. It's three-dimensional. And inside we have a Martini surface. Okay, which I want to. We can build such a Martini surface in such a way that like the induced foliation. So like if you intersect the distribution with the tangent space of the Martini surface, okay, as a closed leaf, closed trajectory. Okay, so that means that like so if you take 2 points on this piece of curve, this curve is a horizontal curve. Okay, and by the way, it's an abnormal curve. Okay, and small enough pieces are locally length minimizers. Okay, so now you see, take this point and take this point. It's maybe just two close points. Okay, first geodesic, here it is. Second geodesic, here it is. Third geodesic. Okay, so you have infinitely many abnormal geodesics joining these 2 points. Okay, so we cannot rule out this possibility. Maybe another corollary of the same type of ideas. Okay, not exactly like this. Maybe another corollary which is related to what was discussed today. So this is with Andrea Mondino. Is that on a closed, say on a compact contact manifold, SubRiemannian, there is at least one closed geodesic. Okay. At least one closed geodesic. And the idea again is to use somehow like information that you have on the loop space coming somehow from this type of reasoning, except that now you have to be a bit careful with the Palais-Mail condition because loops on a compact on a contact manifold, it's not a smooth space. I mean, if you take 2 points on a contact manifold, distinct point, and you ask for horizontal curves joining these 2 points, this is a smooth Hilbert manifold. But if you ask for closed loops on a contact manifold, this is not smooth because constant loops, they form a big singularity inside, okay? But because the singularity is very detectable, you know where it is, you can somehow like implement an analog of the Palais-Mail condition for like using this type of ideas to force the existence of one closed geodesic, okay? Okay, so now in the last 20 minutes, should be, okay, I want to move to the local aspect, okay? Because all this is using global properties of the space, okay? And in some sense, if we take this theorem, so like the fact that we can deform if there is no classical obstruction, okay? It's in a weak sense, okay? But we are not going to be able, at least this is my intuition, to produce with global variational methods new type of geodesics rather than the geodesics we usually find with the classical variational methods, okay? It's good that we could do that, but this theorem says if you apply some type of min-max procedure, you're going to find a normal geodesic, pretty much, okay? And that theorem allows you to use the homotopy of this space, which is the same as the homotopy of this, to do minimax procedure, okay? So in principle, you can combine these two and kind of mimic the classical arguments. But on the other end, there is very special feature arising in SubRiemannian geometry that come from local aspect, local structure of the manifold itself, okay? So maybe the motivating example, so maybe let's erase, we keep these, so maybe we erase this blackboard. So maybe the motivating example is just look at what happens in maybe the simplest non-Riemannian sub-Riemannian manifold, so in the Heisenberg group. So this is just an example now, okay? So now say local structure. So let me consider now the Heisenberg group, okay? So this is the origin, okay? And I take a point over here. So here is a point y. Coordinate, let's say, x, so x is in this plane, and z. So z is a vertical point, and this is the origin. So 0, 0, okay? So now let me look, so this x is in R2, okay? So now let me take a look at the space of horizontal curves joining the origin with y, okay? Now because of this theorem, this space has the same homotopy type as the classical space, and the classical space is contractible, okay? Because we are in R3, so the set of curves joining one point with another point is a contractible space, okay? And so there is no type of like global variation analysis we can play in this space. Space is contractible. If you want to do some type of min-max, there is nothing you could do, okay? On the other end, we know that like to this point, there are many geodesics arriving, right? Maybe this specific point, the picture, I don't know if it's good, but roughly speaking, there are, in this specific case, the number of geodesics arriving at y, okay, is something like 8 over pi x z over x squared, okay? So that means like you can actually compute, in this very specific example, you can actually compute the structure of geodesics, and you can solve for a given point and try to look for how many geodesics there are. So this, it's classic, I mean not classical, but like can be done. We've done this computation with Luca. And you can prove that there are many geodesics arriving at this point. So you see, if if z is fixed and x approaches the 0, so like if this point approaches the axis, the number of geodesics explodes, okay? So these geodesics do not come from a variational argument, because if we do a variational argument, the space is contractible, so there is nothing we could say. And in fact, more generally, maybe it's worth mentioning that this phenomenon of like the number of geodesics growing very fast when you approach somehow the vertical of the distribution is general. So at least maybe I should mention this in the contact case. So if we take, so this is a result with Luca Rizzi. So if we take Darboux coordinates, so we are in a contact with Darboux coordinates on a neighborhood U of a point. So no topology, because this neighborhood we can take it contractible, so the horizontal space is contractible. We can say that like we can, so in Darboux coordinates, a point has coordinate xz, okay? We can say that the limit as epsilon goes to 0 of the number of geodesics arriving at the point, say, epsilon x, epsilon square z, sorting from the origin in Darboux coordinates. This is larger than a constant, so this constant is depends somehow on the point q times this, okay? Maybe plus big O of 1. So it means that like it's a general fact that like you can, at least in the contact case, you can take a point and another point. This you can make the second point arbitrarily close to the first one, and the number of geodesics between the two of them grows unbounded, okay? And you can actually control from below the rate of growth of this number of geodesics, okay? So this is somehow a computation that goes from this right-hand side, which is a computation in the nilpotentization, and on the left-hand side, which is somehow like an asymptotic statement, okay? And somehow what I want to describe now is that this type of statements are always true. So maybe in the more general case, it's going to be more difficult to control the number of geodesics. But if we pass to topology, which in our case for us is good if you remember this inequality, we can control asymptotically the topology of what happens in the of your space with what happens in the nilpotentization. Okay, so I want to make this precise now. So this computation just suggests that there is something that forces these 2 points to have many geodesics. Okay, there is something that forces this to have many geodesics. And in fact, by the way, this formula somehow it's if the point is on the axis, this formula gives infinite, right? Which okay, it's true because we have a family of geodesics, right? In this case, so there are infinitely many. Yes, but and also, but can be made a bit more quantitative if we plug in the energy also. Okay, we can control not just a number, but maybe the topology of the family. But I want to discuss this last thing. So somehow I want to discuss this type of statement. So making an asymptotic statement compared with the nilpotentization in the general case, but with for the topology. For the topology. Okay, so here is, so now I need a piece of notation. So say, so we have our Riemannian manifold, sub-Riemannian manifold, and we fix a point Q. Y, we call it Y0, okay, in M. And we pick a neighborhood of this point with privileged coordinates. So if you don't know what it is, well, for what I'm going to say, it's not really important. Okay, it's just a technical tool we need. But I will tell you like that this is a more general construction. You will see what's happening in this construction. Okay, but it's important that this neighborhood that we take has no topology. Could be as small as you want. It's just your favorite small neighborhood. Okay, so now what we do is when we have these privileged coordinates, we have a family of dilations on this small neighborhood, okay, which we call the neighborhood is U, by the way. Family of dilations. By the way, in Darboux coordinates, these dilations are exactly these. So delta epsilon of xz is epsilon x, epsilon square z. So the privileged coordinates are some type of coordinates which are adapted to the sub-Riemannian structure at this point, okay, and which will allow you to, like, somehow allows you to detect the degree of non-autonomy of a function nearby this point, okay. But for us, in fact, what I'm going to say, it's not really necessary that we have these privileged coordinates. So for what I'm going to say, the fact that these are privileged coordinates, it's only what allows in the end to make computations. But it's a general statement what I'm making. So we have this family of dilations, and we define, so we have on U our distribution, which says the span of some vector fields of K. And we define the distribution delta epsilon, okay, if you want, which is the span of epsilon delta 1 over epsilon star of F1, epsilon delta 1 over epsilon star of Fk. So somehow this family of dilations blows up your manifold, okay, and you basically like move these, so to see the geometry, okay, so here is a neighborhood. So at some point, at this point, there will be a vector field which comes from a vector field which is actually defined over here, okay, and we enlarge it, we make it a bit smaller in order to make this like something which has an order unity, okay. So, but this is a construction, like in fact you can think as we have a smooth family of vector fields depending on a parameter. This is just what actually we know, okay. The fact that in the end, when this parameter goes to 0, we get the nilpotentization. This is a theorem, by the way. It's just the thing that allows us to make computation, because in nilpotentization, computations can be done, okay? But it's a general statement. Okay. So you see, we have now on our manifold a family of sub-Riemannian structures. So there is here is the parameter epsilon. At time 0, we have the nilpotentization. Here at time 1, we have our original structure. And here is the theorem. Oh, by the way, let me just fix one more piece of notation. I'm going to call the omega epsilon y the set of horizontal curves for the epsilon structure. Okay. Horizontal curves to y for delta epsilon. Okay. We have a family of sub-Riemannian structures, and the parameter epsilon keeps track of which element of the family we are in. Okay. Oh, by the way, I did not say the sub-Riemannian. So this is just about the distribution. The metric on this distribution is simply by declaring this to be orthonormal. Okay. So this assume it was an orthonormal basis. These are declared to be orthonormal. Okay. So in this way, we generate the distribution. We decide what's the metric on the distribution. Okay. This construction. Okay. So here is the theorem. So this is with Andrei Agrachev and Alessandro Gentile. Imagine now, first I'm going to explain the theorem with a picture. Imagine now, so now this picture looks similar to my other picture, but now it's not. So now the parameter here is epsilon, okay? And the point y is fixed, okay? So we have here is time 0, and here is a structure at time 1. Then we study all these spaces. So now this at time some epsilon is the set of omega epsilon y, the set of horizontal curves arriving at y for the epsilon structure, okay? So you know what I'm saying? These sets, they might be very different one from the other, okay? But if we fix an energy level, so if we truncate these sets at some energy level, at some point, what the topology of this piece stabilizes to the topology of the time 0 piece, okay? So if we truncate with the energy level, this set at some point inside is maybe outside the energy level, confusion, we don't understand. But if we truncate, it's so everything reduces. It's almost if we, okay, in some cases it reduces to finite dimension, but it's almost as if it reduces everything to finite dimension. Everything stabilizes to this case, okay, to what's happening in the 0 case. So more precisely, for every E value of the energy, there exists an epsilon bar, such that for every epsilon smaller than epsilon bar, these spaces, omega epsilon y with energy bounded by D, they are all homotopy equivalent to what's happening at the time 0. So somehow it says that if you fix the energy, the topology, the amount of topology that you have in this space with energy bounded by E is the same that you have at time 0. Yes?
Do you have an idea of epsilon bar?
No. Well, I mean, no idea. Because the existence of this epsilon bar somehow depends on the number of open neighborhoods that you have to extract from possibly infinitely many open neighborhoods on that cover weak neighborhood cover the ball. So it's about like the number of open sets that you need to do something, okay? Okay, so maybe it's interesting to discuss.
If you only E, then they both will be contractible. If you consider omega epsilon y, it is contractible, and omega of y is contractible. All topological structure comes with E, so that's important. That first you fix E, then send epsilon and epsilon to the simple dependent exchange. If you exchange,
What is the other slide?
you just have a contractible. The order of the
I had one more piece of paper that I cannot find now, but it was here. Okay, here. Okay. Yes, I mean if you ignore the E, everything is contractible simply by what we said before, because they are all homotopy equivalent to the classical one. The classical one in this small neighborhood is contractible. Okay. So still, I mean, at this point, this theorem is not helping. Okay. If you just have this, because maybe here we have no topology. Okay. It is going to help us only if here we have topology. And this is exactly the second point that I want to discuss now, that like here we have a lot of topology actually. So somehow like you see when you perturb, so you can view it the other way around, view this as a perturbation of this. The structure of geodesic, when you perturb a sub-Riemannian structure, gets completely destroyed. But the topology is very stable when we fix the energy. The topology persists, and the fact that the topology persists allows to predict that you have critical points in nearby structures. Okay, so maybe let me just add maybe. So this is so somehow this theorem is the analog of like this step without knowing what's in here. Okay, so this step is saying take the limit as epsilon goes to 0. Something can be counted in the nilpotent approximation. Okay, so then what happens in the nilpotent approximation is the next step. So in the contact case, you can predict exactly the rate of growth of the geodesics. In the general case, what I can say is that there is going to be something predicting the topology of this set. Okay, so a bit weaker in the sense that like counting geodesics, maybe it's more difficult. But in fact, we have a very precise description also of the structure of geodesics over here. 2 minutes, good. But the structure of geodesic over here is very different from the structure of geodesic over here. Just the topology is very close. Okay, so then maybe I want to put this as the last result. Okay. So now we work in a case where so now I'm gonna say something about the nilpotentization. Okay, and the way to pass this information to the perturbed structure is using this. So now we work in the generic nilpotentization. So I take a step 2 Carnot group. Means that like you generate everything with just one bracket, okay, and with some dimension constraints, it's the generic type of nilpotentization that you get, okay. And here is what I want to say. So we have now, here is a bit unusual picture. So now here is the first stratum of the Carnot group, say the distribution, and here is the orthogonal complement to the distribution, okay. Complementary space. So this is a bit larger, okay. So a bit larger. I mean, it's a just to emphasize that, like, I want to emphasize what's happening in the vertical direction, okay? Because I want to mimic the structure over here. So what I can say is that in the general case, so let's say a few quantitative statements about the topology of this space. This space, omega 0, okay, means we are in the nilpotentization. Y E. So the total amount of topology that there is in this space, if we pick E in the vertical direction, grows, this is an inequality at this point, at most as a polynomial of degree corank of the distribution minus 1. Okay, this inequality goes the wrong way for us for now. And then the total amount of critical points, so let me call, say, I'm going to use the cardinality of critical points with energy smaller than E. But it's not cardinality because we have actually critical manifolds. So this means the number of critical manifolds. This grows at most as a polynomial of degree de corank. Okay? But in the corank 2 case, we can say more. We can say more, and this is the crucial part where this inequality becomes asymptotically an equality, one equality. In the corank 2, this is what happens. I'm going to just draw a picture. Imagine now that you plot the Berry numbers of this space. Okay, so here is a plot. Here is I is the index. So this is I. This bi is the amount of topology of this space in dimension I. You plot this. Okay, so this might be a very complicated function. Okay, and everything depends on the parameter E, the energy. So what we know, this is what we know is that when E goes to infinity, in the end, everything disappears because the space is contractible and we have no topology. And this somehow, the area below this plot grows at most as a polynomial of degree in rank 2, at most as a polynomial of degree, grows at most linearly, okay? So what is interesting is that if y is a generic point in the vertical space, it indeed grows linearly, and moreover, there is a limiting profile to this shape. There is a limiting profile to this shape. So like, imagine like there is a wave which is moving to infinity. Everything disappears at some point because the space is contractible. This wave is getting more and more power because it's growing linearly, the total area which is below this wave, okay? Something I did not say is that the amplitude of this wave is not growing, okay? It's actually, yes, it's not growing. So this wave is getting more and more power. And what is interesting is that it has an asymptotic shape in this sense, that the limit as E goes to plus infinity of 1 over E, and then the sum of Berry numbers in a range, so between some range. Okay. So imagine like I am doing a rescaling, so dividing by E, I'm making this constant area, okay? And I'm just looking at Berry numbers in some range, okay, which is moving. Okay, this limit actually becomes the integral of there exists a function, rho. It's like a density of the topology at infinity, such that the amount of topology over here in a neighborhood somehow, like if you rescale by E, is the integral in between C1 and C2 of this function. Okay, so somehow, like in this case, if Y is the generic point, you can actually predict that there is a lot of topology. Okay, and you can actually predict the shape of how the topology distributes among all the range. Of course, when E goes to infinity, everything disappears, and there is no topology. So somehow, like this is just a final word. It's like I would say like what's behind this fact that like in this space here, because the space itself is a small neighborhood, we don't expect to find topology at infinity. The space is contractible. But still there is something that forces the topology. And this something persists if you rescale, okay? And you only see it at infinity. It disappears eventually, but you only see it at infinity. Okay, stop here.